So there's a lot of stuff that follows from this theorem that any two n-dimensional vector spaces are isomorphic that we showed in the last clip. And so we'll talk about a couple of those. So the first one is that any two isomorphic vector spaces have the same dimension. And also, two vector spaces with the same dimension are isomorphic. And if you want to write down the isomorphism, it's actually really easy. You just write down a basis for one and a basis for the other, and they have the same number of elements, so then you just need to give some kind of a bijection between these things that matches up how they are, and that bijection of the basis elements gives you an isomorphism of the vector spaces. So one implication of this idea is given in corollary 361, in which we have that the dimension of the space of linear transforms from V to W is the same as the dimension of V times the dimension of W. And so proof goes as follows. Let's take n to be the dimension of V, so dimension V is equal to n, and m to be the dimension of W, so dimension of W is m. Then we have the following calculation. If we look at the dimension of LVW, that's going to be the dimension of FMN, because we saw in a theorem, so this was, what was that? That was 360. We saw that LVW is isomorphic to FMN. And then this is going to, so the dimension of FMN is MN, and that one was by 340. And that'll do it. So that's one idea, short and sweet. Another idea that's maybe a bit more exciting is that if V is n-dimensional, then it's basically just Fn. So if V is an n-dimensional real vector space, it's basically Rn, and if it's an n-dimensional complex vector space, it's basically Cn. And this means by choosing a basis for V, we can rewrite any linear algebra question so this is any question about linear combinations of things, systems of linear equations, that sort of thing. We can rewrite any linear algebra equation about V or its elements in terms of matrices. So it gives us a very nice computational tool for writing problems down and working things out. So for example, if you were setting out to find a polynomial in P3R such that applying d to p, so that's the derivative, you get 3 minus 2x squared, then you could begin by writing the, say, we're going to encode the polynomial a0 plus a1x plus a2x squared plus a3x cubed. We're going to write this in column vector form, so a0, a1, a2, a3. Okay. And then looking at this question of, is there a p such that dp equals 3 minus 2x squared? Now that becomes a matrix equation where we're trying to solve 0, 1, 0, 0, 0, 0, 2, 0, 0, 0, 0, 3 applied to y0, y1, y2, y3 gives me 3, 0, minus 2. And so I've completely recast this question about the polynomial space in terms of some matrix equation. And this is what we're going to do in the next video.